double integrals over general regions. Let's look below here. It says Fubini's theorem. It says for a function fxy that is continuous on a region D of type 1, we have our double integral equaling an integral here bounded by two functions, dy. Now those functions are functions of x, and those functions of x are the change in y. So what I want to talk about here is I want to talk about that idea of this dy means my change in y. And if I think about this function y here, we know in general y equals fx. And if y equals fx, then if I'm going to talk about the change in y, that means my functions then should be functions of x, and that's what we see here. And notice after that even though I have those functions of x there, now when I get to dx, I have constants. And that's how this works. In essence, what we do is we have a function, and then for our bounds we have a function. For the first integral we do, and then once we go through that process, we only have an expression of x. Then we take the integral of dx of that, and then we get our constants. So the big idea here is if I'm dealing with dy here, my bounds are going to be functions of x. That's the big deal. Now let's go below here. This says similarly, for a function fxy that is continuous on a region D of type 2, we have the same integral. Now notice this. I have a dx here, and I have, for my bounds, functions of y. Now for the same reason the top is, this is going to be my x equaling some function of y. So my change in x is that x there, and those bounds then are going to be functions of y. So that's what we look at here, and that's what we're going to do first. That's one of the more difficult parts of doing these double integrals over general regions, is the fact that I have to set these bounds up, and I have to do them correctly, and not just that, I have to look at them the right way so I can actually integrate them. There's a lot of issues that come up when we don't do this correctly, and that's really going to be the biggest obstacle here when we do these double integrals over general regions. So let's take a look at this problem below here. I modified it some because all it was asking for was you to classify it as a type 1 or a type 2 region. I took it a step further here. So we're looking at this region here. Okay, and it says y equals x cubed plus 1, x equals 0, and x equals 1. So it created this region here, and I wanted you to be able to see this region. Now the second part says find the volume given f of xy equals 4. So all I did was create a horizontal plane. That's all that is, and it's at z equals 4. And the region D. So I want to use this region here to the left. So what we're going to do is we're going to set up this integral. So right away we can say this, and this is at no cost. Now we're going to determine which way to go. Now this is what I want to talk about below here. I think we really got to get our hands on it to know this and see how this all plays together. So one of the things I like to talk about when I talk about setting these up is the fact that, do I have a clear upper and lower function when I look at it in that perspective? So what I mean by that is one function completely above the other one in the entire region, or in the entire interval, I should say, not region, but interval. And if you look at this one here, if I go from 0 to 1 here on the x, the purple one, which is the y equals 1 plus x cubed, is above the y equals x cubed function on the entire interval from 0 to 1 of x. So when I notice this, that tells me right away I'm going to go in that order. Now you might think that it's dx, but it's not. It's actually dy. Now, if that's a little confusing to you, I'll kind of point this out of what's really going on here. Now, when I look at these intervals to talk about this region, I'm looking at this region here. And this region here are definitely my changes in y, because I'm going down to up and up to down idea here. So this is why this would be a dy first. And another indicator here is my y here is equal to some function of x. So that's a giveaway too, that when I have these functions and I don't have to switch them around or anything, that this is going to tell me that how this is going to run. So now the easy part then becomes, once I establish that, I can simply say then that my upper function is going to be 1 plus x cubed, and the lower function is just going to be the x cubed. And then if we look at the dx now, that's what I'm going to do next. Now I'm going to do the dx here. That's just going to be from 0 to 1. So that's the nice thing about that. That usually becomes very easy once I set that up and I establish that order. And from this, we can do these integrals, I think. This is probably your first one, so it's going to take a minute to work through. So just be aware of that. All right. And honestly, no, I don't think you guys can get this if you've never seen it before. All right, so now we got the 0 to 1. We're going to do the integral of the inside because we work from the inside out. Okay, so the integral of 4 is 4x. Oh, not 4x, 4y. Okay, and that's going to be the upper bound minus the lower bound. And then I have my dx next. Okay, so now what we're going to do here is we just take the upper bound, plug it in, minus the lower bound, plug it in, and then we go from there. So this is going to equal the integral from 0 to 1, and this is going to be 4. I'm just going to pull that 4 right out so I don't have to deal with it here. I'm going to get a 1 plus x cubed minus x cubed, because that's when I plug in the second one, and dx. Hopefully that's okay. Now again, I pulled the 4 out, so I'm really just looking at that y, so I plug it in for the first, minus plug it in for the second, and that's what we see here and here. Okay, so anyways, so now this is our setup here. So it's the integral from 0 to 1, because we haven't even touched that yet. This can be cleaned up a little bit. Those are going to cancel each other out, and I'm just going to end up with the 4 here, 4 dx. And then what I'm going to do from here is I'm just going to say now, the integral of 4 is 4x, and that's going to be from 0 to 1. So this is going to actually end up being 4 as our answer for this one. The big thing here was not the actual integral itself, but the setup of this integral, and that's going to be one of the largest obstacles for us for all of these problems here. We'll do some more of them, and hopefully it solidifies as you see a couple more videos. But there's our answer for this one.